Okay, so let's get started. The title of my today's talk is Java Without Future, and the subtitle, Concurrency on Modern Java Virtual Machine. So maybe a couple of words about myself. I'm a senior software engineer working on Jira Cloud at Atlassian. And by my education, I'm a molecular biologist. By occupation, a software developer. I'm also a homebrewer by hobby. You can see some handles and emails. So if you have any questions you want to ask, or you want to find me on LinkedIn, you can also use the QR code for finding my profile on LinkedIn. Please, if you have any questions, want to talk anything, you're welcome to get in touch with me. Okay, so enough about me. Let's talk about Java. Let's talk about concurrency and everything related to it. So let's start with a basic question: how modern computers become faster and faster? And you probably know the answer, which is the Moore's law, which says that every 2 years the amount of transistors on an integrated circuit doubles, right? So that's how it was first coined in 70s, and it actually kept up to date until recently. And it's actually still the same thing, that every 2 years the number of the amount of transistors on an integrated circuit doubles, so that we can get faster and faster computers, faster and faster processors. But you can see a plot of number of transistors on an integrated circuit or on a chip versus time. And yeah, well, basically this is the scale is logarithmic, but you can see that since it's logarithmic, it actually is a straight line. It's a straight line on the plot. And yeah, you might wonder, so if so, why there's anything to talk about if we have faster and faster CPUs? Well, the Moore law is still in effect, but there's one caveat to that. It's that it's the number of the cores in an integrated circuit that is rising. So you can't actually have faster and faster CPU cores. The current trend in software, in hardware, is that instead of increasing the speed at which the CPU works, it's actually increasing the amount of CPUs that can do work concurrently or at the same time. And that's how the CPUs are getting faster and faster at tasks that we throw at them. So the thing here is that to be able to unleash that potential that is in the hardware, we need to start writing software a bit differently. We cannot just issue a sequence of tasks at the CPU. We cannot just write a simple non-concurrent software, because CPUs, as so far, well, they don't know how to split different tasks into concurrent code. It's the software developer or the programmer that needs to bring in their knowledge and develop the software accordingly. So that's the problem that we're facing. And there is also a problem of terminology, because there are actually two terms that are related to multi-threading and programming in a multi-threaded environment. So there is concurrency and parallelism, and I would like to discuss these terms first. So what is the difference between concurrency and parallelism? Concurrency is the problem of scheduling multiple largely independent tasks onto a smaller set of computational resources like CPUs, memory, network interfaces. Let's say we have a large set of tasks, but that might interact with one another, but otherwise are largely independent. and they are all competing for resources of the computer system. The canonical example of that is, of course, server. For example, a web server which answers to HTTP requests. Parallelism, on the other hand, is a completely different problem. It's when we have one job to do, let's say invert a matrix, and we just want to do it faster. And the way we want to do it faster is by employing multiple processing units, multiple CPUs. We break the job down into multiple cooperating tasks, and they all work together to accomplish that one bigger task. And parallelism in that sense is about cooperating on a single thing. And concurrency is about different things competing for resources. For example, in Java, parallelism is probably best served by parallel streams. So you can have a stream, invoke some operations on it, but when you call the finalizer operation on that stream, if the stream is set to be parallel, this task will be executed on in parallel on different CPUs for each element of the stream. So that's how you can achieve parallelism in Java. What about concurrency? And that's what I want to talk about today. So the problem is this: when we write the server, like the one that I mentioned before, an HTTP server, what we would like to have is a high throughput. So this means that we'd like to have a high number of requests handled per unit of time, say per second. In fact, if we write any server and we want to do things concurrently, classically what we've done in Java since Java 1.0 is to accept a request and service it, start it, and finish on a single thread. So you start, accept a connection from the socket, assign a thread to this request, serve it all the way until the end, until you flush the answer from the buffers, and then once you're finished, that thread might be returned to some pool, but during the processing of a request of a transaction, we hold on to a single thread. And the problem with that is that the number of transactions we can process at one time is then limited by the number of threads. And while you can have, on a modern server, you can have around 1 million of open sockets, maybe even more, it's just not feasible to have 1 million threads. We can have, say, 2,000 threads, 4,000 threads, or 5,000 threads. I think that's around the maximum number of requests that you can handle concurrently if you use threads for that. Even though your server could hypothetically support 1 million requests at the same time, because you can have up to 1 million open sockets. Like, for example, a WhatsApp server, the WhatsApp application, the instant messaging application, the engineers working on that applications, they're claiming that they can handle 10 million connections at one time on a single server. But that's because they use Erlang, which has a different concurrency model than Java, and it doesn't employ threads as we know them as Java developers for dealing with this issue. So the question you could have, well, why Java virtual machine can't be like Erlang? Why can we have only such a small number of threads? And the answer to that question is that in OpenJDK, in the project that develops the virtual machine, and is the most popular virtual machine, Java threads are just thin wrappers around operating system threads. And that's pretty much for every well-known, used virtual machine. It's pretty much the same with J9, the virtual machine from IBM, or other virtual machines around, Java virtual machines around. So, as I said before, Java threads are thin wrappers around operating system threads, and operating system threads are a very precious resource. Modern operating system can support more than a few thousand active threads at a time. And there are various reasons for that. So if that is the style of programming you want to write in, you're limited by the number of threads. So what people do because of that limitation, they say, okay, so we're not going to service the entire request from start to finish on the same thread, but rather we're going to do some processing, like accept the connection, do some processing, return the thread to the pool to be used by other transactions. And then let's say we dispatch an outgoing request to a microservice, and when the answer comes back, then we'll continue it possibly in another thread. And that style of programming is called asynchronous programming. And there are various libraries commonly called reactive that are meant to make that easier. For example, RxJava. For Spring Boot supports this style of programming. And this solves the throughput issue. So with reactive programming, you can get to the maximum throughput that your hardware supports. But then the way you write your software, your program, is not harmonious with the design of the platform, because everything about the Java platform is built around threads. If you have an exception, the troubleshooting context you get is the thread stack, right? So it's like the central concept in the model of execution of Java code. Once you use those reactive frameworks, the thread stack you get doesn't really have any valuable information in it, any useful information, because the same task really moves from one thread to another, and you cannot step through those requests or transactions in the debugger, because the debugger steps through operations on a single thread. So while if you use asynchronous programming, your action actually moves from one thread to another, and you can't get actionable profiles using profilers because they group operations by thread. So that's another issue. And the profilers just don't know about asynchronicity of your code. So it doesn't know about asynchronous transactions. So the truth is that you're fighting the platform left and right. Actually, you as a Java developer are faced with a choice. You can write code that's harmonious with the design of the platform, and it won't be scalable. And then you will waste money on hardware because you will need more servers just because of the thread limitation. Or you can make efficient use of the existing hardware with asynchronous programming, but then you're going to need to waste more money on development and maintenance, because developing and maintaining and observing an asynchronous software is so much harder. So what I want to talk about today is a Project Loom, which is supposed to break that dilemma and let you write code that is simple, that is harmonious with the platform, and lets you use tools that you already know, that you already like, tools like debuggers, profilers, to get the same kind of actionable information that you get today. So the idea behind Project Loom is to make it possible to use the full potential of the hardware that you have, to not bring asynchronicity, and at the same time have the same throughput as you do with asynchronous programming, like with, for example, RxJava. So yeah, let's talk about how the competing platforms solve the issue so that we can have the full landscape of what's happening and why Java needs to change. Why are those changes made to the Java virtual machine? one thing that comes to my mind is JavaScript. And Node.js, which has become very popular recently and is a contender to take place of JVM. There's no doubt about that. So if you're programming in JavaScript or in TypeScript on Node.js, every time you define a function that returns a value by invoking a callback, you just made an asynchronous function. So asynchronous functions return values, and asynchronous functions do not return value. Instead, they invoke the callback or callbacks that you pass as one of the parameters of that function. And synchronous functions give the result as a return value, and asynchronous functions give you it by invoking a callback you pass to it. So you can't call an asynchronous function from synchronous one, because you won't be able to determine the result until the async one completes later. And the problem with async functions is that they don't compose in expressions because of the callbacks. They have different error handling and can be used with try-catch blocks or inside a lot of other control flow statements. And the thing with Node is that the core library are all libraries are all asynchronous. And when people talk about callback hell, they're talking about how annoying it is to have async functions in the language. Today, I did a research, a quick research on NPM, and there is almost 15,000 libraries for doing asynchronous programming. So they're trying to cope at the library level with a problem that language forced them into. So that's one problem, or one way of solving the asynchronous problem with using callbacks, but that's not really a solution, I believe. So yeah, one thing that people in the Node community have realized is that callbacks are a pain, and they have looked around for solutions. And actually, we have a similar solution in Java. It's called promise, and in JavaScript world, it's called future or completable future in Java. What is a future? It's a wrapper around a callback and an error handler. So if you think of passing a callback and error handler back to a function as a concept, a promise is basically a reification of that idea. So it's a first-class object that represents an asynchronous operation. And in my opinion, it's snake oil, because promises or futures, they make asynchronous code a little bit easier to write. They compose a bit better because you can use then, but honestly, it's like, it's a bit less painful, but I don't think it's something that you should get really thrilled about the value proposition, because you can still use them with exception handling or control flow statements. You still can't call a function that returns a feature from synchronous code, but well, you do, but then if you do, the person who later maintains your code will not be happy with that. So it's just bad style to do this. And you have still divided your entire world into synchronous and asynchronous halves, and you have all the misery that entails. So even if your language features promises or futures, it's still a problem. So I've mentioned Java and JavaScript, but there are other languages that do that in a similar way. For example, Python. So one way to deal with that, with features, or another way of dealing with the asynchronicity, is the syntactic sugar of async and await. I think of the bigger languages, the C# was the first one to introduce this syntactic sugar, and it's already in modern ECMAScript as well. So you can use this await keyword to invoke an asynchronous function. So this lets you make asynchronous calls just as easily as you can with synchronous ones, but you just need to add this tiny little keyword. You can nest await calls in expressions, use them in exception handling code. You can stuff them inside control flow, and that's nice. It makes a lot easier to write asynchronous code, but you know, you still have the world divided into two. Those async functions are easier to write, but they're still async functions. So synchronous functions return values. Asynchronous functions return some kind of a wrapper around that value, like future or promise. Synchronous functions are just called. Asynchronous functions need to have this await before the actual invocation. If you call an asynchronous function, you've got this wrapper object when you actually want the object itself. You can't wrap it unless you make your function asynchronous and await it. So yeah, I would agree that it is better. But the problem is still there. As soon as you start trying to write things like higher order functions or reuse code, you're right back to realizing that the distinction is still there. And if you have an asynchronous function used somewhere in the bowels of your code, you need to pull it up to the highest level, because this distinction between synchronous and asynchronous is bleeding all over your code base. So yeah, it's some kind of a solution, but it's still not the best solution in my opinion. Let's take a look on how Go deals with that problem. It uses a simple concept that is called goroutine, and it's quite similar to Erlang or other esoteric languages, because in Go we have goroutines, which are functions or methods that run concurrently with other functions or methods. And you can think of them as lightweight threads that have nothing to do with operating system threads. So they are, well, you probably might have heard about green threads. So these threads are very lightweight, and the cost of creating a Go routine is very, very teeny when compared to a thread. And it's common for Go applications to have thousands of Go routines running concurrently. It's pretty much similar with Erlang. I've mentioned before that WhatsApp, in WhatsApp, a single server can handle 10 millions of connections at a time, and it does with 10 millions of lightweight Erlang threads that are not operating system threads. And this is basically what Project Loom is about. It aims at introducing a similar solution as goroutine or Erlang threads, and they used to be called fibers. They are called virtual threads now. So what are they? What are virtual threads? From the perspective of you as a Java developer, or from the perspective of Java developer, virtual threads are just threads. They're Java threads. So their semantics are exactly the same in terms of pretty much everything, but under the covers, unlike today's threads, which are now called platform threads in Project Loom, they do not map to one-to-one to operating system threads. So a virtual thread is not a wrapper around an OS thread. Rather, it is a Java runtime construct that the operating system doesn't know anything about. Under the covers, the runtime, which is the libraries, the core libraries of the JDK and the virtual machine, they map a great many of those virtual threads, even millions, onto a very small set of operating system threads. From the operating system perspective, if you run a program, your program might be running, I don't know, 8, 32 threads. And from your perspective as a software developer, as a programmer that developed that software, you will be running a million threads, and those threads will be virtual. The name virtual was supposed to evoke the same connotation and an association with virtual memory, where you have some abstract, cheap, unlimited resource like virtual memory or virtual threads, and that is then automatically and cleverly mapped to some more limited physical resources like random access memory of the system or operating system threads. So that's why they are called virtual. And you might wonder, okay, so if I can have many more threads, if I have more threads, I will have more of the problems associated with threads, right? That's a great question, actually. So first of all, you need to understand that when we miniaturize something, or I think it's better to say right-size something, the difference in scale alone can have a qualitative difference. I mean, even though technically you could think of a smartphone as if it were a miniaturized mainframe, the experience is quite different, right? So the problems to solve are different just because of the form factor, and because a smartphone normally just has one user, it doesn't have all the problems that a mainframe has, like managing batches from multiple users. And the same thing is with threads. In large part, many of the problems that we've had managing threads is because they were costly, and we wanted to avoid overcreating them. And because they were costly, we had to pool them and share them. And that has been the source of many issues when working with multiple threads. I want to give you 2 examples. One is thread locals. So once you share threads in a pool, you have to be very, very careful if you use thread locals, and you probably do because libraries you use, like some login library, for example, they use thread locals. And a thread local is associated not with the task, but with a thread that is executing that task. So if a thread is shared among many tasks and you're not careful, your thread locals can leak from one thread to another. And that, in fact, could be, for example, a security problem, because you could leak a secret from one user to another one. So that's one issue. The other issue, interruption. So interrupting a thread. If you submit a task to a thread pool through an executor service, you get back a future, a wrapper around a possible value in the future. And say you decide to cancel the task that is going to give you that value. So it has already been started on some thread. What that's going to do is to try to interrupt the thread that is executing that task. But because threads are shared, by the time the thread is actually interrupted, it's possible that it is executing a different task altogether. So that means that everywhere where you deal with interruptions, you have to consider the possibility that you have received an interrupt that is not aimed at you, but some other task. So everywhere we deal with interrupts, we need to handle spurious interruptions. And those problems are entirely a result of tasks not being mapped one-to-one to threads. that's what goroutines are about. That's what Erlang is about. The fact that we need to share our threads because they are so costly. But with virtual threads, they're cheap enough to just have a single thread per task. And since we can use cheap virtual threads and have a single thread per task, we don't have those two particular problems. Well, we actually won't have many other problems as well, because once the thread captures the notion of the task, working with threads becomes much simpler. And I think basically this is the right size for thread. One single thread should be one single task. So even if you have many more threads, I believe that this will make working with threads much easier than having fewer threads. Okay, so you might wonder, how do I get started with Project Loom? How do I actually get so many threads running on a Java virtual machine? And that's quite easy. So what you need to do is go to OpenJDK wiki, which is at the address wiki.openjdk.java.net. So if you go there, there's a list of projects in the menu bar here, and you just go to Loom. And then if you go to Loom, there's this getting started section. And the easiest way, they say, it is to start using Project Loom or Java virtual machine with Project Loom enabled, is downloading a build. So this is Java SE version 18, which is early access. So that's not production ready yet. Don't think of using it on the production. It's just for playing with it and figuring out how it works, but not for production yet. There are many issues or open bugs still, but it's good enough to start playing with it on your development machine. And you can download an installation package from this site, and then you just configure your IDE to start using this JDK that has Loom enabled. So I will jump back to IntelliJ, and in IntelliJ, I already have this. I'm sorry, it's not this. I already have this JDK enabled. So I'm going to remove 1.8 and use 18, and it uses 18, JDK version 18. And then you can start working on your code. For example, what's the good use of the many threads that you can use? One thing that Project Loom brings is a very small change in the API. And that's making executor service, the one that you use for thread pulling and so on and so forth. It makes it auto-closable. So if it is auto-closable, what you can do is you can start developing something that is called structured concurrency. So you probably know that you can use try with resources in Java. So I'm going to do exactly that. I'm going to write a try block. And I'm going to use an executor service. So I'm going to executors, and I'm going to use virtual thread pull. New virtual thread executor. I'm going to assign it. Okay. Executor service. Like this. And then I can use this executor service for submitting some new tasks, like print line, hello from a virtual thread, right? So this needs to be a lambda, like this. And now what we can do, let's do it. Let's simulate some concurrency, because we have some code that tries to access console, so it's input and output code. So let's make it concurrent. I'm gonna just invoke this many times. Like 10,000 times, and I++. So you can see what I'm trying to do here. I'm trying to have 10,000 threads on a regular MacBook Pro, and that will just work because we're using virtual threads. So if I run it, yeah, we need to compile it, and you can see it just works. And now, because I'm using a virtual thread executor, we could actually try to time it, but just to give you some impression of how different that might be, I'm going to use static pool. So I'm going to use executors. Fixed thread pool, let's say 32 threads, and let's run it. Yeah, so why would you use this kind of executor service in a tray catch? The one nice thing about it is that it actually won't finish until all the tasks in the executor service in the pool are finished. So if you submit something and then this executor service can be closed thanks to having this auto-closable implemented, it won't actually close until all the tasks in the pool are finished. So this lets you structure the concurrent code and use blocks, which is a basic unit of software of Java language. It lets you structure this code, and then if you're rereading that code later on, it lets you to more easily reason about it. So yeah, that's how you can get started. There are some examples on the web page that I already mentioned on the JDK wiki. So if you go to Loom project, you can see that there is getting started, and then there is this section structured concurrency that explains how to use this this new feature of executor service, because it has been retrofitted to the extent auto-closable. And yeah, it's really fun to see what can you achieve with this simple change. Okay, I guess that's pretty much it. That was the demo. Thank you very much for being with me here today. Just one thing to mention is that currently we're hiring in Poland. Atlassian is hiring in Poland for remote positions. The office is in Gdańsk, but all the software development positions are currently remote. So if you go to this first link that is described by the QR code, you can find the jobs listing. If you want to talk about working at Atlassian with me, again, a QR code for my LinkedIn account. Please, let's get in touch. Let's talk about it. And yeah, I guess that will be time for questions.